actually make sense. Okay. So this afternoon, we're going to start with example number 6, which is halfway through these things. Example 6 reads as follows. If in figure 6, the friction between the block and the incline is negligible, which means that the friction can be neglected, so we don't have to worry about friction. So if they say that the friction is negligible, basically the friction is equals to 0. How much must the object on the right weigh if the 200 Newton block is to remain at rest? So we have this 200 Newton block, and there's this particular object on the right here. So the requirement is that this guy, the 200 Newton block, should remain motionless. And how much then should this be if that is to remain motionless? So we have got two objects here. It's not just one object, but you've got two objects which need to remain motionless. The 200 Newton block and also this particular object on the right, they need to remain motionless. So we need to make sure that these two objects remain at rest. Now, how are we going to do that? The first thing to be aware of is that what you have here is an incline. This is an incline. And as is always the case with an incline, you put some particular object, like this case, the 200 Newton box on an incline. The weight of this particular box is going to be acting downwards like this. So where on your notes, the ones you have printed out, so you indicate that the weight of the object, this box, is acting downwards like that. So it should act downwards that way. Indicate that the weight, this 200 Newton weight, should be acting downwards that way. Okay. After that, what other forces are acting on this particular object? So this object, first of all, we have said this object needs to remain at rest, and also this object needs to remain at rest. So these two objects, this 200 Newton this 200 Newton box, and also this, they need to remain motionless. So after we have identified that this should not move, this should not move, we next identify what forces are acting on these particular objects. So the first one, of course, is the weight. The weight of this box is pointing downwards this way. The weight is acting downwards like that. Then the other thing is the tension in the rope. This rope is preventing this box from sliding this way. So this rope is pulling the box in this direction. So there is a force, there is a tension which lives in this force, and from this end it's acting in this direction. So indicate a tension which is acting in that direction. Then of course the other thing is, apart from the weight of this particular box acting downwards, the weight of this box is exerting a force on the incline. So the incline is not going to be happy. So the incline is going to be pushing back against the box, and it pushes at 90 degrees. So the incline will be pushing at 90 degrees in that direction. So the incline is going to be pushed against the box in that direction, and this is going to be the direction of your normal force. We have got something which shows how the weight, one of the diagrams you have, it shows you how the weight is supposed to go down, then the incline is supposed to push in this direction. I think if I can go back quickly, I can show that. Here, this. So the weight is down this way, 200. The weight is down that way, 200. Okay. Then this is the normal force. The normal force is going to push against the box at 90 degrees in that direction like that. Then of course there is a rope which is attached to our, so I wanted to show this normal force. Say you draw a force pointing in this direction, then of course the weight is going to be pointing in that particular direction. Are we clear? So you're supposed to be drawing right now. Okay? So there are three forces acting on this box. There is the weight of the box pointing down. There is a normal force pointing in this direction. There is a tension pulling on the rope like this. There is no friction because we have been taught to neglect friction. So three forces are acting on this box. Next, if we move on to this particular object, which we have here, this particular one, of course, has got a weight. So the weight of that particular object is pointing down. So you indicate that this weight, the weight of this object, is pointing down this way. So the weight of this object wants to cause this object to move down this way. So there's a weight pointing down this way, but also there is tension in this rope which is preventing this weight from going down. So there's a tension pointing up. So you indicate a T here, Ft. So there's a tension here which is pointing up. So you indicate that there's a tension which is in this particular side of the rope which is pulling up, which is pulling this particular one up. There is also a tension here which is pulling this particular rod up this way. Since we are talking about the same rope, the tension in these ropes, on this side of the pulley and the other side of the pulley is the same because the rope is the same. So the one thing which we know here is that the tension in the rope on this side of the incline and on the other side of the pulley, the tension is the same. We don't know how much it is, but it's the same. So we have identified the weight of this box down. We have identified the normal force pushing against this box. We have identified the tension pulling the box up this way for this particular object. We want this object to remain at rest, but we have also identified which forces are acting on this object. When it comes to this particular object, we have identified the weight of this particular object pointing down, so you indicate the weight pointing down. We have also identified a tension in this rope pulling this particular object up this way. Next, we draw an XY plane over this particular box. So the center of this box is going to be the center for XY plane. So parallel to the incline along this rope, that's going to be our x-axis. Along this rope, that's going to be our x-axis. Then perpendicular to the incline, that's going to be our y-axis. So you draw an XY plane over this box. Parallel to the incline, that's going to be your x-axis. Perpendicular to the incline, that's going to be your y-axis. Then above the incline, we choose above the incline, the y-axis above the incline to be the positive y-axis. So you indicate plus y above the incline here. Then below the incline, you choose the y-axis below the incline to be a negative x-axis. So when you draw an XY plane like this and like that, the y-axis, this side, is going to make an angle with the weight of this box. The y-axis, this side, if you draw your y-axis from up here going down this way, your y-axis here is going to make an angle with your weight. The angle between the weight of the box and the y-axis, negative y-axis, that angle is going to be your 35 degrees. So basically what we are looking at is the following. We're looking at something which looks like this. This angle here. So this bit here, this is going to be part of your y-axis, negative y-axis. So negative y-axis above that side, positive y-axis, then along like this, this is going to be your x-axis. So this angle here, the angle between the weight and your y-axis, this angle is going to be theta. And in our case, this theta is the same as the angle which you have here. So that angle from our diagram, you can see that that angle is going to be 35 degrees. You need to be drawing. So you should have printed these things out so that as we are explaining, you also do things on your end. So we have chosen parallel to the incline to be our x-axis, perpendicular to the incline to be our y-axis, above the incline to be the positive y-axis, below the incline to be the negative y-axis. The angle between the weight of the box and the negative y-axis, that angle is going to be theta, which is going to be 35 degrees. Are we clear?
Yes, sir.
Next, If this rope was not there, to stop this box would most likely slide in this direction. Okay? So if the rope was not there to stop the box from sliding, this box would slide in this direction. So we choose the direction in which the box is likely to slide as our positive x-axis. So our positive x-axis will be down this side. So our positive x-axis will be down this side. Our negative x-axis will be this side. Are we clear? If you have things on a table and things are not moving, always choose the direction in which this particular object is likely to move to be your x-axis. So we have our x-axis in place like this. This is your y. Up, above, that is your positive y. Below, negative y. This side, that's your positive x. This side, your negative y. You do the same thing. You come over here. You draw an xy plane. So this is going to be the x in this side. This is going to be x. Then this is going to be your y. So x will be this side. Your y will be this side. So in this particular case, there is no need for you to, because the object is only moving along the y. So you can choose whatever you want. If you want to choose this side to be your positive x, you want to choose that side to be negative x, that's up to you. If you choose this one to be positive, you choose this one to be negative, it doesn't affect anything, because the only forces acting on this particular box, on this particular object, are acting along the y. Whatever you choose, if you choose this side to be your positive x, so you end up having a tension which is at 90 degrees from your positive x, and you end up having a weight which is at 270 degrees. If you choose this other side to be the positive x, you end up having this guy here, the tension pointing up, that's going to be 90 degrees, then you end up having a weight which is still going to be at 270 degrees. So your choice of x, this side, doesn't really matter very much. On the other hand, since you have chosen our x to be this side, and we should stick to that, your normal force is going to be point up, so your normal force is going to be making an angle of 90 degrees with a positive x-axis. Then the tension in this rope is going to be making an angle of 180 degrees with the positive x-axis. Then the weight of the object will be down this side. But if you have your xy plane like this, in this direction, so you're going to, if you start from this side, you go 90 up to here, then 180 up to here, then 270 up to here. Then since your weight is down here, you add the extra 35 degrees, so you're going to end up with 305 degrees. That's going to be the angle which the weight makes with the positive x-axis. Are we clear?
No, sir, too fast today. About the question, sir.
Yes.
Are we restricted like on the other mass which is supposed to go down? Like if we move the rope, like when choosing the conversions, like x should be positive and maybe to the left it should be positive. Like you have suggested that where it's supposed to fall, that's where you're supposed to choose. That should be your positive x-axis. So are we restricted to that, or
there is a difference between something falling through like this? If it's falling like this here, this is your y. You would assume like something is flat. So this is just your y-axis along here. This is your x-axis in this direction. So what we are talking about here is an incline, something which is an incline like this. Yeah. So with that, assuming that you have drawn your x-axis here, y-axis, then x-axis like that, then you would now work out a table of components. So in this particular case, you start with the weight. The weight is going to be equals to the weight of the box on the incline. That's going to be equals to the weight of the box. Now you remove this sine 35 degrees. The weight of the box, then scrap out the 35 degrees. Then you put cos 305 degrees. Okay, so the weight of the box times cos 305 degrees, because what we have is 270 plus 35, so you have 305. So the weight of the box here multiplied by cos 305 degrees, that's going to give you 200 times cos 305 degrees. So you're going to end up having 114.7, which is just 115. So scrap out this. The cos 35 degrees, you scrap it out, you put sine 35 degrees, scrap it out, you put cos 305 degrees, then you end up having 200 times cos 305 degrees, which is going to give you 115 newtons. Similarly, you scrap out this negative, scrap out the negative here, then it's going to be the weight of the box sine 305 degrees, which is going to give you, scrap out this negative, cancel out the negative, you're going to have 200 times sine 305 degrees, which is going to give you minus, what do you have here? Minus 163.8, which is just basically 134. So replace the sine 35 degrees with cos 305 degrees. Same thing here, replace this sine 35 degrees with cos 305 degrees, then remove this negative here, then replace this cos 35 degrees with sine 305 degrees, then remove this negative here, replace this cos 35 degrees with sine 305 degrees, then you're going to end up with this, and you're going to end up with that. Are we clear? Is it clear?
Yes, sir. Sir,
Yes?
I don't know if you can just explain on the 305 how it has come about, like my network went.
The 305. What we have is something which looks like this. When you draw your x-axis along parallel to the incline like this, okay?
Yes,
Then you draw your y-axis perpendicular to the incline. So at the center of this box, you put your x-axis parallel to the incline, then you put your y-axis perpendicular to the incline like that.
Yes,
The weight of the box is always pointing down this way. So what you notice is that the weight of the box is not along the y-axis. The y-axis is this line.
yes,
At 90
yes,
degrees to the box, to the surface of the box. The x-axis is this way. Then we said if you cut the rope, the box will move this way. So we choose the direction in which the box is likely to move to be our positive x-axis. So we measure our angle like this. So we start from this side, we measure our angle up to here. This is going to be 90. Up to there, that's going to be 180. Up to this point, that's going to be 270. You see that?
yes.
But for us to reach where the weight is, there's this extra angle here, theta. You've seen this?
Yes.
This extra angle theta is the same as the angle of the incline. So, up to this point, up to this line here, this is 270. So 270 plus 35 degrees, that's going to give you 305 degrees.
Okay.
Yes.
Okay.
Is
Thank
that
you
clear
very
to
much,
everyone?
Now I understand.
Is it clear to everyone? That's why we said print out the notes, then follow the instructions as we say, draw this line on that on your printed notes, then draw this line, then mark this angle and all that stuff. Okay, so where are we? Yeah. So so the weight. So here we end up having the weight of the box, which is equals to 200. Then cos 305, that's going to be 200 cos 305 degrees. It's going to give you 115 newtons. Then scrap out this negative, so it's going to be the weight of the box sine 305 degrees, which scrap out this negative, which is going to be 200. Then sine 305 degrees, which is going to give you minus 164. Then when it comes to the normal force of this particular, the normal force always acts perpendicular to the incline. So the normal force would be in this direction, up like that. Since we have chosen this side to be a positive x-axis, so our normal force will be making an angle of 90 degrees to the x-axis. Is that clear? Is that clear?
Yes, sir.
So it's going to be, where are we? We've taken ourselves back. So it's going to be the normal force. So you put Fn here, right? Fn cos 90 degrees. So Fn cos 90 degrees, that's going to give you 0 newtons. So in front of these 0 newtons, put an equal sign, write Fn cos 90 degrees, that's going to give you 0 newtons. Then for the y component, you're going to write Fn sine 90 degrees, that's going to give you Fn. Are we clear? So this side,
Yes, sir.
somewhere there, write Fn cos 90 degrees, that's going to give you 0 newtons. Then this side, you write Fn sine 90 degrees, that's going to give you Fn. Then when it comes to the tension where it is, if we have what we have chosen is down is going to be positive. So you can see the tension in this rope will be making an angle of here up to here is 90, up to there is 180 degrees. So the tension will be making an angle of 180 degrees with our chosen x-axis. So when you do that, we can work out what's the x component of the tension. So it's going to be Ft. So before here, right, Ft, the tension, cos 180 degrees. That's going to give you minus Ft. So Ft cos 180 degrees, that will give you minus Ft. Then for the y component, you write Ft, this side here, right, Ft sine 180 degrees, that's going to give you 0 degrees. Is that clear? So that takes care of all the forces acting on the box on the incline. The weight and its components. This is going to be the component of the weight, the x component of the weight, the y component of the weight. The normal force has got no x component, but it has got a y component, Fn. The tension in the rope is going to have a x component minus Ft. The y component is going to be 0. So once we do this, the next thing we do is we add the x components. That's going to be 115 newtons plus 0 newtons plus minus Ft, and we add the x components and make sure that when you add these x components, they should give us 0. So when we do that, we end up with the following. The sum of the forces along the x-axis, the x components, should be 0. So we're going to end up having 115 newtons plus 0 newtons plus minus Ft. That's going to give us 0. That's going to be 115 minus Ft equals to 0. So we end up having Ft being equals to 115. So we end up having the following. You're going to end up having Ft being equals to 115. So the tension in the rope is going to be equals to 115. Are we clear? Is it clear to everyone?
Yes, sir.
Next, you add the y components. This bit minus 164 newtons plus normal force plus 0 newtons. So you add the y components again. No one needs to tell you to add the x components. Or you just simply add them and make sure they're equal to 0. Once you do that and you add them and make sure they're equal to 0, then the stuff you want to find out will start coming out. So in this particular case, so you're going to end up having minus 164 newtons plus Fn plus 0 newtons equals to 0. So you end up having Fn, the normal force, being equals to 164 newtons. Okay, so this is all you can do for this bit here. For this particular object. You do this, you've done this for this program. That's all. There's nothing else to do. Then you move on to you come and do the same thing to this particular one. So this one has got a tension which is up. This one has got a weight which is pointing down. So you draw an XY plane here. So this side, in this particular direction, the horizontal direction, that's going to be your x-axis. Then the vertical direction, that's going to be your y-axis. Like I said, in this particular case, you choose whatever you want to be a positive x. Whether you choose this side or you choose that side, it doesn't really matter very much, because the forces which are present are simply acting up and down. So if you choose this side to be a positive, fine, then the angle between the positive x-axis and this tension here is going to be 90 degrees, and if you're moving like that, then the angle to the weight is going to be 270 degrees. If you choose this side to be a positive y-axis, x-axis, then the angle between the positive x-axis and this tension here is going to be 90 degrees. Then if you go around like that, you're still going to end up with 270 degrees. So you find the components of the tension and the weight or acting on this particular object. So there must be another table. Okay, I haven't put it there, but that table is supposed to be there. So basically, what you're going to find with the other table is that you end up with, there will be no x components. There will be no x components to the weight. There will be no x components to the tension. But what you're going to end up having is the following. You're going to end up having, I think we have got a table similar to for this side. I think there should be a table similar to that somewhere. Where is that? The table for the tensions, not this one. I think here the table. This one, yeah, this small table here. This small table here is for this object. So it's the same thing, because you've got a pulley, then there's a tension in this rope, then there's a weight. So you make a table, a small table for that particular object, like this one here. So you put in the weight. For the weight, FW, so it's going to be, the x component is going to be FW cos FW cos 270 degrees. That's going to give you that should give you 0 newtons. Then FW sine 270 degrees, that should give you minus FW for that other thing. Then for the tension, you're going to have Ft is going to be equals to, for Ft, you're going to have the x component to be Ft cos 90 degrees, that should give you 0. Then the other bit should give you Ft sine 90 degrees, that should give you 1. So you end up having minus Fw for the weight. So the weight is going to have the x component to be 0, 0. So there's nothing you can do about the x components. But for the y component, you're going to have a weight which is minus Fw, then you're going to have a tension which is Ft. So you add the tension and the weight, and you make sure the equals to 0. So you're going to have minus Fw, which is the weight, plus the tension Ft equals to 0. That's going to give you the weight. That's going to give you Ft being equals to the weight. Now when Ft is equals to the weight, we already know what the tension is. The tension is, we have found to be 115. Where is that? Here. The tension was already found to be 115. So at the end of the day, you come to the conclusion that the weight of the object needs to be 115 for the object to balance. Are we clear? So you need to have another table. There needs to be another small table created for this part. For this part. So just copy the one which we have up there. Then you work out, you indicate the x-axis horizontally, then the y-axis perpendicularly. Then you work out the components for the tension, which is going to be here, Ft. Then the components for the weight, which is going to be pointing down like that. So the weight, the y component of the weight should be minus Fw. The x component of the y component of the tension must be Ft. So you add up Ft plus minus Fw, that should give you 0. That's going to give you Ft equals to the weight of the object. And since we know what Ft is from this side, it's 115. That is basically what the weight is going to be. Are we clear?
Yes, sir. Sir.
Yes.
If the tension at tension 1 and tension 2 are the same,
Tensions are
say
always the
that,
same. They're always the same.
yes, yes, sir.
They're always the
Now,
same, but they
can
point
we
in different directions.
yes, sir. Now, can we also say that the two masses are moving at the same with the same acceleration?
They are not
Let's say
moving.
maybe
The question doesn't say they are moving. The question
just wanted
says
to
they are not moving. If in figure 6 the friction between the block and the incline is negligible, how much must be the object on the right way if the 200 Newton block is to remain at rest? So they're not moving. Are we clear?
sir, I'll just yes.
Any other question? Okay, so that brings to the end of us looking at how to apply the first condition of equilibrium. Now, the next thing which we need to do is we need to learn how to apply the second condition of equilibrium. And for us to learn how to apply the second condition of equilibrium, we need to be able to work out how much torque a force is causing. And when we're talking about torque, we are basically saying how much turning effect does a particular force cause. So here we've got a very good example of what we mean when you're talking about torque and lever arm. So this is a very, very good example. So here we have got a bar. This is a bar. It has got a length of 80 centimeters, and there are a bunch of forces acting on this bar. There is this force, 25 newtons, acting at an angle of 25 degrees. There is this force, 20 newtons, which is acting through, whose line of action is the same as the pivot. There is another force, 10 newtons, which is acting at an angle of 90 degrees. And of course, there's this point here, A. This point A is basically what we call a pivot, which is the center of rotation of this particular bar. So you have got something which can rotate. You've got a bar which can rotate, and what we are trying to do is we are trying to find out how much turning does each of these forces cause. Now, the other thing which I want to bring to your attention is we have spoken about something called the lever arm. The question is, what do we mean when we say lever arm? Because once you know what the lever arm is, for you to find out the torque, you simply multiply the force times the lever arm, then you know how much torque it is. Okay. Now, I want you to pay very, very close attention to what I'm going to explain. There is something called the line of action of a force. Basically, this is the direction in which the force is acting. For example, if you take this 25 Newton force here, this 25 Newton force, as you can see, there is this extra dotted lines they are putting there. This is the direction in which this force is acting. So for each force, there is always a direction in which that force is acting. Now, if this is the line along which the force is acting, then you decide to draw a line from the pivot. You decide to draw a line from the pivot up to the line of action of the force, which is this line. Then you meet this line, using this line, at an angle of 90 degrees. This angle here. You need to meet this line at an angle of 90 degrees. When you draw a line from the pivot up to the line of action, then you meet at an angle of 90 degrees. This line, which meets the line of action at an angle of 90 degrees drawn from the pivot, this is what is referred to as a lever arm. Are we clear? This line, which meets the line of action of a force at an angle of 90 degrees here. This line is what is referred to as a lever arm. Once you know what the lever arm of a force is, you simply multiply the force times the lever arm. Then you find out how much the torque is. The other thing to look at all this lever arm business is the following. You have got this bit here. This is 80 degrees. Then there is this angle which has been made here, 25 degrees. Then there is this line which goes that way. Then this line which goes that way is met at this point by this lever arm. So what you notice, what you have is a triangle, a right angled triangle, where this end here is a right angle, a 90 degrees angle. So what you have ended up having is a right angled triangle here, whose hypotenuse is 80 centimeters, and which makes an angle of 25 degrees. So we are simply asking you, find the opposite of this triangle. The opposite of this triangle is your lever arm. So for you to find the opposite of this triangle, that's going to be sine 25 degrees equals to the lever arm divided by your hypotenuse. So that's going to give you a lever arm which is equals to what? So sine 25 degrees is equals to lever arm divided by hypotenuse. So the lever arm is going to be equals to the hypotenuse, which is the length from the pivot up to where the force is acting. So the distance from the pivot here up to where the force is acting multiplied by the sine of this angle. So a straightforward way to find the lever arm in this particular case, if you want to find what the lever arm is, you simply you look at where the pivot is, you go all the way up to where the force is acting. So you get this length. This is the 80 centimeters. Then you multiply it by the sine of this angle. When you do that, you're going to get your lever arm. Once you have your lever arm times the force, this gives you torque. Are we clear?
Yes, sir.
So the lever arm keeps on changing. In this particular case, in the case of the 10 Newton force which you have here, the distance, the line of action of the force is along this line, like this. Now, if I draw towards any other direction, I can't make 90 degrees. The only way I make 90 degrees is if I draw a line from here, going straight through this bar up to here, and that's why we are being shown this 90 degrees here. You see this 90 degrees here? This 90 degrees is telling you that the length of this bar is the lever arm for this particular force. So you draw from the pivot straight up to the line of action of the force, and you make sure that you have a 90 degrees angle. That's going to be a lever arm. So for this 25 Newton force, the lever arm is this bit here. That's going to be 0.8 meters times sine 25. That will be a lever arm. Then lever arm multiplied by 25. That's going to give you a torque. For this force here, which is 10 newtons. So that's going to be this distance up to there. That's going to be 0.8 times sine 90, which is just going to give you 0.8 times sine 90. That's going to give you 0.8. Then you multiply by this, you're going to get your torque. The interesting part is this force here. This force, 20 newtons. Now this force 20 newtons, as you can see, the line of action of this force passes through the pivot. If a force passes through the pivot, that force does not produce any torque. Are we clear?
Yes, sir.
If a force passes through a pivot like this one, whose line of action, if you extend this line, it will pass through here, then that force cannot produce any pivot at all, any force, any torque at all. So that's how you work out torques. You need to find the lever arm. Sometimes it's obvious, sometimes it's not so obvious. Like in this case, if your force is acting at 90 degrees, then it's just the length, the distance from the pivot to where the force is acting. That would be your lever arm. Otherwise, if your force is not acting at 90 degrees, you need to multiply the distance from the pivot to where the force is acting times sine this angle. The angle which the force makes from the pivot from this point to there, and the direction in which the force is acting, like that. You could also do the same thing with this bit here. You could say, okay, fine. The lever arm, the lever arm is going to be from here up to there. Then the angle is going to be 180 degrees or 0 degrees, whichever one it is. As long as it's 180 degrees or 0 degrees, you say sine 0 degrees, you get 0. Sine 180 degrees, you get 0. So this force, 20 newtons, does not produce any torque. So that's how you find the size of the torque. The next thing about torque is what direction is this force going to cause this bar to turn. This force, the 10 Newton force, will try to turn this bar this way. Okay, so indicate that this 10 Newton force will try to turn the bar in this direction. This direction is a clockwise direction. This force here, the 25 Newton force, will try to turn the bar in this direction. So you indicate like that. Say this force will turn the bar in this direction. That is an anti-clockwise direction. This one does not produce any torque, so we can't worry about direction because it doesn't produce any torque. Since this particular force passes through the pivot. Are we clear on how you work out torque? You need to know what the lever arm is. And the straightforward way of finding out the lever arm is as follows. You choose what's your pivot, you look at the pivot, you look at where the force is acting. The distance from here to where the force is acting, you need that distance, that's your R. Then you see what angle does the force make with this. At what angle is the force acting? If it's acting at 25 degrees, so you multiply this distance times sine 25 degrees. If it's acting at 90 degrees, then you multiply this distance times sine 90 degrees. If it's acting, like in this case, the angle is 180 or 0 degrees, you multiply times 0 degrees, 180 degrees. Then you get what your torque is. So once you get the size of the torque, the other thing we're interested in, of course, is what is the direction. The direction of the torque, if the force is causing an object turn this way, then you indicate with your pencil, say, this force, this 10 Newton force, will cause the bar to turn in this direction. If it causes the bar to turn in this direction, that is a clockwise torque. If it causes the bar to turn in that direction, that is an anti-clockwise torque. So once you have a clockwise and an anti-clockwise torque, it's up to you. You choose which kind of torque is going to be positive, which one is going to be negative. If you choose clockwise to be positive, then that's it, which means anti-clockwise is going to be negative. Are we clear? Are we clear? So for the first force, the 20 Newton force, so it's going to be the force you're applying times the distance from the pivot to where the force is being applied, which is 0.8, then multiplied by the angle. The angle is 0 degrees or 180 degrees, so you end up with 0 Newton meter. So that's how much torque is produced, nothing. The reason why, it's because the line of action of the force is passing through the pivot. Then you've got the 10 Newton force. The 10 Newton force, which you're going to call, whose torque we're going to call tau 2, that's going to be 10 newtons times the distance from the pivot to the point where the force is being applied, which is 0.8, then sine 90 degrees, you're going to end up with this 8 Newton meter. Then there's a 25 Newton force, so that's going to be 25 newtons times 0.8 meters times sine 25, you're going to end up with 8.5 Newton meter. Are we clear? Now there's something which is very interesting you have to see here. Look at this. We had a small force, 10 newtons, but our small force was acting at an angle of 90 degrees. And it produces this much torque. Then we had a bigger force, 25 newtons, then it was acting at an angle of 25 degrees. Then it produces a torque which is almost the same as this. Almost the same as that. What this is telling you is that a force will produce maximum turning effect at 90 degrees. A force will produce maximum turning effect at 90 degrees. That is why when you are trying to untie a tire, the nuts of a tire, using a spanner, you put your spanner on level so that you stand on it on this other side. So that when you step on the spanner, you put it level. Okay? So that when you step on your spanner, you will be applying a force at 90 degrees. That is the one which is going to produce the most turning effect. So if you see mechanics trying to untie tires, they always put the spanner at 90 degrees horizontally so that they can step on it. They can use their weight of the feet to step on the thing. Are we clear? Is there any question on how you work out torque? This is the force you're applying. F is the force you're applying. R is the distance from the pivot. So F, so torque is equals to F R sin theta. So in this particular case, F is the force you're applying, whether it's 10 newtons, 20 newtons, or 25 newtons. R is the distance from the pivot to the point of application of the force, which is here. This distance from the pivot or the axis of rotation to the point where you're applying the force, that is your R. Then your theta is the angle between the line of action of your force and your R. This angle, that's your 25. This angle here, that is your 90 degrees. Then in this direction, your angle is just 0 degrees. So that's how you work out the torque. You find the size of the torque. If the torque causes an object to turn in a clockwise direction, then you say that's a clockwise torque. If it causes an object to turn in an anti-clockwise direction, then you say that is an anti-clockwise torque. Then you choose what should happen. If you clockwise is positive, you stick to it. If you anti-clockwise is negative, you also stick to it. Okay. Any questions? We can't continue to have another question. We're almost out of time. Unless I can push it. But I don't know. We can push it. We have how many minutes? We have about 8 minutes. Okay, fine. Let's try. So here, 7. A uniform bar of length L weighs 200 newtons and holds a 450 Newton object as shown in figure 8. So the bar, which is this bar here, it has got a weight of 200 newtons, and the weight of the bar acts through the center of mass or the center of gravity, which is what we are shown here. The weight of the bar is pointing down here, 200 newtons. Okay, then it has got another object which has got a weight of 450, which is this bit here. The 450 Newton object is this one here, pointing down. Okay, the question is, find the magnitude of the torques exerted about the forces as shown in the figure about the two supports at the end. So what are the forces? The two supports are these ones. So this bar is going to be pushing against these knife edges, but these knife edges are going to push back. So there's going to be these forces, F1 pointing up this direction, F2 pointing up in that particular direction. So as shown in the figure of this, like this. Okay, fine. So the first thing which you need to do is, in a diagram like this, the first thing you need to do is you need to identify clearly. In this particular case, we don't have any forces pointing along the x-axis. We only have forces pointing along the y-axis. So what you're going to do here is you're going to add all the forces pointing up in the positive x-axis. So you make a choice. You say, okay, fine. Up is going to be positive, down is going to be negative. Okay? Then you make a choice. The choice you're going to make is the following. You're going to say, okay, fine, up is going to be positive, down is going to be negative. So this force here, F1, is going to be a positive force. This one here is going to be a positive force. But this force here, the 200 Newton, force is pointing down, so it's going to be negative force. Then this force here, the 450 newtons, is pointing down, so it's going to be negative force. So one of the equilibrium conditions says that the sum of the forces along the y-axis should add up to 0. So we're going to add that. So the sum of the forces along the y direction should add up to 0. So the positive forces along the y are the F1 and F2. Since you have chosen F1 and F2 to be positive, so you indicate, say, up is going to be positive, down is going to be negative. So this one is going to be positive force, this one is going to be positive force, this one here is going to be negative force because it's pointing down, this one is going to be negative force because it's pointing down. So you're going to end up with the following. You're going to end up with the following situation. You're going to end up with F1 plus F2 plus minus 200 because it's negative plus minus 450 equals to 0. So you're going to end up with F1 plus F2 equals to minus 200 minus 450. So that's going to give you the following. It's going to give you F1 plus F2 equals to F1 plus F2 minus 650 equals to 0. So you're going to end up with F1 plus F2 equals to 650. This is what you get by applying the first condition of equilibrium. Are we clear? Is it clear?
Yes, sir.
Next, we need to apply the second condition of equilibrium. But for us to apply the second condition of equilibrium, we need to be able to work out a torque. But for us to be able to work out a torque, we need a pivot. Are we clear? For us to apply the second condition of equilibrium, we need to be able to work out the torque. But for us to be able to work out the torque, we need a pivot so that we are able to measure R and we are also able to measure the angle theta. So you have a choice. Like in this case, it's not obvious which point should be the pivot. You can choose any point. You can choose A here. You can choose you can choose this point to be a pivot. You can choose this point to be a pivot. You can choose this point to be a pivot. It's not obvious. The reason why it's not obvious is because if I choose the point A to be the pivot, there is only one force passing through this particular point, which is F1. So F1 will not produce any torque. Are we clear? Are we clear?
Yes, sir.
If I choose A to be the pivot, there is only one force passing through this point, which is F1. So F1 will not produce any torque. But this one will produce a torque because it's going to be, if this is the pivot, we've got a distance from there to there. The distance is going to be L over 2 multiplied by this particular force times the angle here is 90 degrees. Then next, this distance from here to there, you're going to have L over 2 plus quarter. That's going to be your R. Then you multiply by the force, which is what you have here. Then the angle, which is 90 degrees. Then from this side to there, you're going to have L. So you're going to have this guy pointing up, whatever the force is, then the angle 90 degrees. So you can work out what the torque is. So these guys, this force and this one, they'll be trying to turn your bar in this direction. This one will be trying to turn your bar in this direction. This one will be trying to turn your bar in that direction. So you're going to have this force trying to do this force trying to turn this one here. So this one will produce a clockwise torque. This one will produce a clockwise torque. This one will produce an anti-clockwise torque. If you choose this point to be a pivot, so the weight will not produce any torque, but you're going to end up having F1 doing something this side, this one doing something this side, this one doing this side. At the end of the day, this is not a good choice because what you end up having is you end up having F1 plus F2, which you do not know. Because you don't know what F1 is, you don't know what F2 is. So you need to remain with only one thing you can work out. One of the forces, one of these forces. If you choose this one also, there's only one force passing through here. So you end up having F1 producing a torque, this producing a torque, this doesn't produce a torque, this produces a torque. But you still remain with F1 and F2, which you do not know. Because remember, we have said F1 plus F2 equals to 650. So if somehow we can work out one of the two, then we can find the others. If you choose this point here, again, there's only one force passing through it, which is this one. So this force will not produce a torque. So you end up having worked out torque from this side. So the distance from here to there, then the angle 90 degrees, then the force, you find the torque, then the distance from here to there, which is half, then the angle 90 degrees, then the force, you find the torque, then the distance from here to there, which is quarter, then the angle 90 degrees, then the force 450. So the good choice of torque of pivot is either this point A or this other end here. Why do we say that's a good choice? Because at the end of the day, if we do that, we don't have to work out, if we choose this to be the pivot, then we don't have to worry about this one, because this one will not produce any torque. If we choose this one to be the pivot, then we don't have to worry about this, because it will not produce any torque, because any force passing through the pivot does not produce any torque. Are we clear?
Yes, sir.
So we will choose point A to be our pivot. If we choose point A to be our pivot, then we don't have to worry about F1, because F1 is passing through the pivot, therefore it won't produce any torque. So the torque due to F1 is going to be equal to 0. The only other forces which will produce a torque will be the 200, then will be the 450, and this other bit here. The force produced, the torque is going to be the distance from the pivot to here, which is L over 2 multiplied by the 200 times sine 90, which is the angle here. Then the distance from here to there, that's going to be 3/4 or whatever it is. Then times the weight, the force, which is this, then times sine 90, which is going to be in this direction. The direction in which these forces are going to be turning, causing the bar to turn this way and that way, that will be clockwise. So this one will be clockwise torque, this one will be clockwise torque. When it comes to this particular force here, the distance from here to there, that will be the length of the bar. Then the angle between this, the line of action of the force, and that will be 90 degrees. So you're going to have sine 90, then multiplied by the size of this force, which is whatever it is. So it's going to be an anti-clockwise torque. So the whole point of the second condition of equilibrium is you add the clockwise torques plus the anti-clockwise torques, and you should end up with a 0. So you need to choose which ones are going to be positive, which torques will be positive, which torques will be negative. If you choose the clockwise torques to be positive, then the anti-clockwise torques are going to be negative. If you choose the anti-clockwise torque to be positive, then the clockwise torques are going to be negative. Are we clear? It's up to you what you choose. So in this particular case, the clockwise torques, all of them, torque 1, that's going to be 200 times the length, which is L over 2, times the other thing we're not including, sine 90 degrees. Sine 90 is just 1. So if you want, you can put sine 90 there, here. In between the plus sign and thing, you can put sine 90, which is just going to give you 1. Then plus 450 newtons, then 3 over 4 L times sine 90. So you're going to end up with the clockwise torque being equals to 437.5 Newton times the length. Then the anticlockwise torque is going to be equals to, which is torque 2, is going to be the force, which is F2 times the length times 90, which is what you're going to get there. Then after that, you decide what you're going to do. So in this particular case, we say, okay, our clockwise torques, we'll treat them as positive. The anticlockwise torques, we'll treat them as negative. Then we add our torques. So when we add the torques, we're going to have the clockwise torques plus the anticlockwise torques. They should give us 0. So the clockwise torques will be this much. Then plus, since we have chosen clockwise to be positive, plus, then the other torque, which is this one, which is anticlockwise, is going to have a negative sign. Minus Ft minus F2L equals to 0. Then you get this guy. So you end up having 437.5 newtons. L minus F2L, you take it to the other side, you're going to end up having F2L is equals to 437.5 N multiplied by L. There's an L on both sides, so you can cancel out the L, which basically tells you don't need to know the length of the bar. So you're going to end up with F2 equals to 437.5 newtons. So if F2 is equal to 437.5 newtons, then you can go back, because remember what we had. We had F1 plus F2 equals to 650. So if F2 is equals to 437.5 newtons, then you put your F2 there, then that will allow you to find out how much F1 is. So you're going to end up with the following. So F1 plus F2 is equals to 650. Then your F2 is that. So you want to find F1, so you take this to the other side. So you're going to have F1 is equals to 650 minus F2. Then your F2 is 437.5. So you're going to end up having F1 is equals to 650 newtons minus 437.5 newtons. And when you get that, the difference is going to be F1 is going to be 212.5 newtons. Are we clear?
Yes, sir.
Yeah. So we have gone above time by 5 minutes, but I think it was worth it. Any questions?
Sir.
Yes. Is there any question?
No, sir.
All right. If there's no question, then we'll meet on Thursday. Okay. So I've come to the end.
Thank you, sir.
Yeah. Please print out these things. Make sure you're going to print out so that when you're making corrections, you also make corrections on your end.